Welcome to the first video for SLO10. In this video we'll be looking at what really amounts to an unusual kind of a result that we observe when we react nucleophiles, like in this case a Grignard reagent, with certain kinds of carbonyl electrophiles, and specifically carbonyl electrophiles that are what we call alpha beta unsaturated. So this would be an alpha beta unsaturated ketone. In the previous SLO, we saw other kinds of alpha-beta unsaturated products, including alpha-beta unsaturated aldehydes. We also called those enals. So really, in these kinds of systems, you do get what you would expect as the addition product, like the way we learned about this in SLO6, and this is the major product. But an appreciable amount of another product forms, and that is the product that still has a carbonyl in it. Looks like this, which is a little bit surprising. So this is the minor product. For this particular alpha-beta unsaturated ketone in this particular Grignard reagent under these particular conditions, it's about 60% this compound and about 40% this compound. Those percentages will vary widely depending on the structures of the nucleophile and electrophile. But what I want to do in this section of this video to get us started with SLO10 is to try to understand how this minor product actually formed. To get started with that, I'm going to actually try to figure out what bonds were actually formed in the reaction. And I can trace this ethyl group onto this position here. We might call this the beta carbon. So I'll put in my Greek letters again, alpha and beta. And that means that I'm making a new CC bond to the beta carbon. So new CC at beta carbon. All right, so the next step I'm going to take is try to decide how this happened from a polarization perspective. Or in other words, what kinds of roles am I using here to make this new carbon-carbon bond? It's probably the case that the carbon that's attached to the magnesium in my ethyl magnesium chloride is nucleophilic. We've talked at some length about why that would be. And so if I think about how this bond forms, and I think the ethyl group is going to be my nucleophile, then that means the beta carbon had to have been my electrophile. But I don't understand how that's possible. There's not a leaving group. There's not like a polar bond, like a CO bond that I could break, like I've done for other addition reactions with carbonyls, for instance. So I'm kind of at a loss about how this happened. So the next step I would take would be to think about the actual structure of alpha-beta unsaturated ketones or aldehydes or esters, whatever, themselves. So we'll do a little bit of structural, structural analysis of alpha-beta unsaturated carbonyls. We'll keep it general. So we have like an alkene that's conjugated to a ketone or an aldehyde or an ester or an amide, you get the idea. And I'll just choose this compound as an example, but what I want to focus on are the parts of the molecule that will be essentially conserved for all compounds I would describe this way. So that means that I have a double bond adjacent to a carbonyl. So that would be like the subunit I really want to focus on. And then I'll put in some methyl groups so I can actually look at the structure itself. So what I'm trying to do is rationalize how I could have electrophilicity at the beta carbon. That's my job. I'm going to do that by assessing electron density. So none of this should be too surprising, right? We've used this framework all semester long. And I'm going to do this in two stages. I'm going to consider induction and I'm going to consider resonance. Those are the tools that I can use to distribute charge in a molecule. So from an induction standpoint, so induction at the beta carbon, I'm not really seeing much here. So there is a CO dipole, so I have withdrawal that way, but that's kind of far away from the beta carbon. So if anything, I've maybe got a very weak inductive withdrawing effect from kind of the carbonyl substituent. So carbonyl is weak inductive acceptor. Okay, So, and then we'll say this is for proximity reasons. But this inductive effect would be even more powerful at the carbon of the carbonyl itself, like we've talked about kind of ad nauseum at this point in the semester. So really, like, I should just get this, right, just the major product, but I don't. I get appreciable amounts of this other thing. So the other thing I want to consider then is resonance. So I'll do some resonance analysis. And what I want to focus on is how I can manipulate electron density at the beta carbon specifically, right? So the carbon here at the bottom of the alkene that I've drawn. And I could do one of two things. I could move electron density toward that carbon, but that wouldn't explain apparent electrophilicity. So I'm going to try to use the experimental results here to actually focus on seeing if there's some way that I could remove electron density from the beta carbon using resonance. And it turns out that there is. I can take this CC double bond and move it toward the carbonyl, and by doing that, break the CO pi bond and place a lone pair on the oxygen. So another way of saying that is that my carbonyl is a resonance acceptor of electron density. So resonance at beta carbon, carbonyl is a resonance acceptor. And just to make sure that we can see that in all of its glory, I'm going to draw the resonance structure that would correspond with the analysis. So my sigma bonding framework is all going to be the same. We decided that there'll be a third lone pair on oxygen. That makes the oxygen negatively charged. It looks to me like we'll be forming a, wow, it kind of looks like an enolate, weird. And then finally, we'll have a positive charge on the beta carbon, which is exactly what we were trying to explain, right? So this resonance analysis, what I can say is that the beta carbon of these alpha beta unsaturated carbonyls is actually quite electrophilic because of this resonance effect. So beta carbon is often electrophilic in alpha beta unsaturated carbonyls. We hadn't seen this in the case where there was no double bond, and if I removed this CC double bond for some reason, maybe I like hydrogenated it or something like that, this resonance effect wouldn't exist, right? So this is really only going to be true that the beta carbon is electrophilic if this is a conjugated system, if I've been able to connect the beta carbon to a carbonyl or something like a carbonyl, something that could remove electron density by resonance through this conjugated system. So in the next section of this video, we'll look at a couple of examples where we actually take advantage of the fact that these beta carbons are pretty highly electrophilic. And what we'll find over the course of this SLO is that we've actually developed reactions that are even selective for what we call a 1,4 addition over a 1,2 addition. So we're ready to look a little bit deeper into this other kind of addition process that we hadn't seen prior to our analysis of these alpha-beta unsaturated carbonyls. And to get started, I want to actually distinguish them using a handy piece of nomenclature. So the reactions that we've learned so far that would give us products like this, we're going to call these 1,2 additions. So 1,2 addition. And these numbers don't tell me necessarily about nomenclature in the sense that you would name a molecule using the IUPAC rules. They're relative numbering of the atoms involved in the pi bonds that break. And so if we look at a 1,2 addition, we see that what happens is that we're breaking a bond between essentially oxygen and carbon, so 1 and 2. But if we kept numbering our chain through the conjugated system, remember it's that conjugation that's important here, then we end up with a situation where the alpha carbon would be 3 and the beta carbon would be 4. So if I add the nucleophile to the beta carbon, or in other words, carbon number 4 in this kind of numbering system, we call this a 1,4 addition. Essentially, it's like the number of atoms that are spanned by bonding changes because of this addition. So there's other names for this, right? 1,4 additions are also sometimes called conjugate additions. So you can use those two terms interchangeably. I tend to favor 1,4 addition, but they mean the same thing. And the conjugate addition is a little bit nice because it reminds you how important conjugation is for it to actually work. There's open names too. We'll learn one more that's usually used for a slightly specific case of a 1,4 or a conjugate addition, and it carries someone's name. So we'll see that a little bit later on in this video series. So let's look at a couple of specific examples of 1,4 additions. So pretty much any nucleophile can do this, as long as the electrophile is appropriate for conjugate addition. So remember, conjugated system. So we could look at kind of a silly example. We could look at hydroxide, which is a nucleophile, as we've learned. And we'll just choose a really simple alpha beta unsaturated carbonyl electrophile, just this enal. And so one of the things that can happen here is that the hydroxy group could add to the beta carbon, and that will give rise to a product that has a beta hydroxy group. Okay, so that would be one option. This reaction is reversible, right? So this looks a lot like the intermediate that we use to go from an aldyl reaction to an aldyl condensation. So we have this kind of a process, right? We could look at another example. We could use an amine nucleophile. So again, we'll choose relatively small molecules for this. The idea isn't to know like this specific reaction, but see a kind of a general trend. So let's look at this reaction. So alpha beta unsaturated ketone in this case is our electrophile. And the same process applies. The nitrogen can add to the beta carbon, and electrons move up into the carbonyl. So the carbonyl is really activating the beta carbon as an electrophile here. And because it's doing the activating, it's going to end up with the electrons once this new nitrogen carbon bond forms. And it was true when we formed our new oxygen carbon bond. So that would give us a product that would look like this initially. So this part probably would be reversible. I could imagine reforming the CC pi bond by elimination, and this nitrogen, when it's positively charged, should be a fairly good leaving group. But one of the things that we notice here, and I kind of made a joke about it in the previous section of the video, is that this intermediate, actually both of these intermediates, has what looks like an enolate. And that enolate can do chemistry. So we learned in the last SLO that enolates come from removing protons from alpha positions to ketones or aldehydes or esters, right? pKa's of things like 20 or 25. So these are actually pretty strong bases. And in this case, what we would see is an intramolecular, or maybe a solvent-assisted proton transfer. And that part's probably effectively irreversibly because of the difference in pKa's, right? So I'm going to be making something that has a pKa of 20, but I'm starting with this acid, which has a pKa of 10. Remember, these are ammonium ions. So this is highly favorable. And so we end up with a final product that looks like that. So like a beta amino ketone. And so this reaction actually works pretty well, right? So oxygen anions, it's kind of a mixed bag, really kind of depends on the position of equilibrium. In these kinds of situations, this works reasonably well, where we can add amines in a conjugate fashion, or we can do 1,4 additions of amines to these alpha beta unsaturated ketones. So one of the other takeaways I just want to make sure that we have up on the board here is that there's an intermediate that forms when we do conjugate addition, and that intermediate is an enolate. Enolates are intermediates from 1,4 addition. And we will see examples where that's kind of an important concept here shortly.